Today we will begin our first major unit of Calculus 3, namely the vector function. So in the introductory video for this course, I mentioned that we can basically split the course into three major parts. Based on the three major types of functions we're going to deal with specifically to this class. The first one, the vector functions, are functions which associate a vector to a real number. It's very important in this class to always have an analogous example or a default example from real life that illustrate the tool or the object of discussion. So let's start right away with the definition, and then I'm going to talk about the default example that you should have in mind when we go over this chapter. So a vector function, as I mentioned already, associates a vector in component form. Again, this is either in R3 or R2. Typically I use R3 examples, but remember what I mentioned in the beginning: if there is no specific remark made about it, you should assume that most of the concepts are analogous, so you don't have to define the same concept all over again for both 2 dimensions or 3 dimensions. So obviously the 3-dimensional one is the more general one. So a vector function associates a vector in component form to a real number, and that real number I'm going to denote it by t for a good reason, which I'm going to talk about in a moment. So you start with a real number, okay, and then you associate a vector. And of course, if it's in component form, that vector will be denoted by our typical notation for a vector in component form. So the typical notation for a vector function is going to be the way we denote a vector in component form, that is a variable with a bar on the top. But now, because this is a function, is going to be of t, right? You're going to specify its argument t. And then the components of the vector which represents this function should depend on t as well. So you're going to represent this by old-fashioned real valued functions. Let's say f of t, g of t, h of t. All right. So to each t, you're going to associate a vector, which of course its components will depend on t as well. And obviously, if you want to use the standard basis notation, you can write it as a linear combination of the standard unit vectors I, j, and k. So the default example from real life that you should have in mind is that this function describes a motion of a particle in space. In other words, it gives you the trajectory of that variable as time goes on. That's why we typically denote t the variable by t, because in this default example, t denotes the time. So it's so useful to have this default example in mind that even though it doesn't have to represent always a motion in space, I still usually call the t the time variable. Now, let's see how we can actually graph this, because we're going to spend this first section on representing, how do we represent, of course, these types of vector functions. And an important remark that I want to mention right from the bat here, make sure you actually watch the Maple examples, and better yet, make sure you run them on your own. In fact, you should use a computer algebra system to run the examples on your own. Maple or something similar. It doesn't have to be Maple, but that's what I'm going to use in the class. Because as always in Calculus 3, there is very limited drawing you could do by hand. I'm not particularly talented on that as well. You don't have to. Visualization is 90% of the work. You just have to draw enough to actually figure out the rough sketch of the figure, but everything else, anything better than that, should be done with the technology. All right, so a vector function, like roughly speaking, right, you have a domain which is the real numbers, right? So the domain for t is the real axis, right? This would be the domain. So notice that you cannot actually represent the function and its domain, I mean the value of the function, which is a vector, and its domain in the same coordinate system, right? Because the value of the function is in 3D. So the value of the function for every t is going to occupy, this is x, y, and z, is going to be in 3D. So this is the domain over here. And then let's say the trajectory that I was talking about looks like that. And let's say for a given t, the corresponding r of t is over here, let's say. So to each t, you're going to have a corresponding vector in component form r of t. Because it's in component form, it starts from the origin. So for that reason, because this vector essentially points from the origin to the position of the particle on the trajectory, this r of t is also called, in this context of a motion in space, the position vector, right, at time t of that particle. Again, if you imagine this is a motion in space. So for example, let's say you are at a, after a later time, t plus h, that's how you'll come up with the derivative of this function. We'll talk about that in the next section, next lesson. Then maybe the position vector is over here, right, as the particle moves from left to right in the way I sketch it here. So you could see that it's not really practical actually to sketch the domain. Most of the time we can make do without specifying in the graph, I mean without labeling in the graph the actual or sketching the real axis. You could mention the time value on the point itself, on the trajectory, as I'll show you with some examples later on. So typically we are happy just with the trajectory. Sometimes we also indicate with arrows the direction of motion on the trajectory to actually figure out how the motion goes from our perspective, from left or right, or this is in space, of course. It's not just left and right, but twisting up and down and so on. So what about some examples of vector functions? Well, as it turns out, you already actually know an example when we derived the parametric form of the equation of a line. Let's say a line that goes through the point x naught, y naught, z naught, and in the direction of the vector ABC. So if you remember, the parametric equations of a line were given like this. X equals x naught plus TA, TB, and same thing for all of these coordinates, right? But if you think about it, you can view this, I mean, in the vector form, you could basically say that for every t, you basically have a position vector that indicates the corresponding point on the line with the component x naught plus AT, y naught plus BT, z naught plus CT. And in this case, of course, t takes any real number. So the domain is all real numbers, right? Because it's an entire line, right? So if you have a line like that, each r of t indicates the position vector on that line as t varies. So that's about basically the simplest example of a vector function. And intuitively, since you already went through calculus 1 and 2, you should realize that linear functions are easy to deal with, right? I mean, all of these, you have t at power 1 in linear combinations, right? So this is a linear function because obviously it's the equation of a line. But the reason also I mentioned this as a starting point is because often you may want to actually produce just a portion of a line. Okay, so the domain, in other words, the domain of the parameter does not have to be all real numbers. What if, for example, let's say, you know, in a certain type of motion, let's say the particle goes on a straight line, then it goes maybe on a semicircle, and then maybe on another straight line a little bit steeper like that. Okay, so so for example, let's say this happens at t at some moment of time. Let's say t equals 5, let's say this is t equals 10, t equals 12, and so on. So obviously you may have to actually figure out a way to represent the equation of a segment of a line. Okay, so the question is, how do I actually represent, using a vector function, the equation of a line segment? So in other words, a line that doesn't extend indefinitely, but just goes from a starting point, let's say, of coordinates x1, y1, z1 to the point x2, y2, z2, right? Let's say in this direction like that, okay, from the left point to the right point. So let's see how we can actually do this. The formula is quite simple and is very well known for those who, you know, once you start working with these equations. But it's sort of those things in which, just for the purpose of reviewing our previous concepts, it's worthwhile to actually go over the main way to obtain it. So let's stay tuned for the next page. All right, so I sketched the line here again, this line segment. So let's actually start by finding the equation of a line just by using our formula before. You should have the formula sheet in front of you with the equations of these formulas that we learned already. This is in particular particularly important to my students because that's how I teach it, right? So I expect you to have the formula sheet with all the formulas we learned so far as a reference in front of you. So for the equation of a line, let's use x1, y1, z1 as a starting point, as a given point, in other words. Remember, that equation requires a given point on the line, whichever you prefer, and also the direction of the line, which is a vector parallel in the component form, parallel to the line itself. How do we find a vector given 2 points on the line? Well, the easiest thing is to just translate x1, y1, z1 at the origin. So the direction of the line vector is going to be x2 minus x1, y2 minus y1, z2 minus z1. Remember always, don't confuse the point with the actual vector. Lots of people sometimes get confused here. So notice the round parentheses. I mentioned 2 points. A component vector in the direction of this line can be obtained by translating the original point, the given point, to the origin. That is to say, you subtract it from the coordinates of the terminal point. And this will be the direction of the line, which is denoted by ABC in the formula that we used in the previous sections. So what is the equation of the line? Well, the first component is going to be, so it's going to be x equals x1, the starting point, plus the parameter t times the component, the first component of the direction, y equals y1 plus t times y2 minus y1, and same thing for z. This is the full line. Now the question is, what restriction should I make on the domain for t so that I get only the line segment, not the full line that extends on both sides of those points? And if you look carefully, let's see. Yeah, I mean, if I let me see how I can do that much faster. Yeah, so let's actually rewrite it a little bit, and then I'll give you immediately the domain. So let's rewrite these parameters by grouping the x1s, y1s, and z1s together. So notice if I distribute the t, the first equation actually is x1 plus tx2 minus tx1, and then I can factor out x1, which gives me 1 minus tx1 plus tx2. And obviously the same thing works for the other variables. 1 minus ty1 plus ty2 so on and so forth, 1 minus t z1 plus t z2. So if you look carefully, notice that if t is replaced by 0, I get precisely in this parameter parametric forms, right? I get precisely x equals x1, y equals y1, z equals z1. So t equals 1, position yourself, you know, t equals 1 corresponds to the initial point of that line segment. And on the other hand, if t equals 1, then the parentheses will cancel, and then that gives me x equals x2, y equals y2, z equals z2. And that gives me the terminal point of that line segment. So it turns out that if you write the equation of the line in the manner I just wrote it here, as it turns out, if t goes from 0 to 1, so if you go from 0, look at the picture here on the top corner, if you go from 0 to t equals 1, as it turns out, you just basically go over the entire line segment from that initial point to the final point. You can write this in a more compact form, the way we can write it even in a more compact form. If you denote the position vector that points to the initial point by r1 and the position vector that points to the terminal point x2, y2, z2, then the line segment formula for the equation of the line segment will be r of t equals 1 minus t r1 bar plus t r2, with again t between 0 and 1. Alright, so this will be one formula that is, you know, you can put it in the formula sheet. And notice that the direction of motion matters, right? If you want to go from x2, y2, z2 to x1, y1, z1, you simply interchange r1 and r2. Or you go in reverse, t from 1 to 0. But obviously, usually the domain is, for the real axis, goes from left to right. Let's do a quick example. Let's say I want the line segment from the point 113 to the point 032. All right, so the position vectors will be 113. Again, it looks like I write the same thing, but it's not really the same, right? I'm talking about the actual vector pointing to that point. That's why it has the other notation with the brackets 113 and 032. So it's a straightforward problem, obviously, right? So the segment will be given by 1 minus t scalar multiple. That's a scalar multiplication, by the way. 113, 1 comma 1 3 plus t scalar multiple z 032. And it is customary to bring everything into a single vector after this. So do the scalar multiplication and addition. 1 minus t times 1, 1 minus t times 1, 3 minus 3t, added to 0, 3t, 2t. So altogether, r of t will be 1 minus t plus 0, 1 minus t plus 3t, that makes it 1 plus 2t. And then 3 minus 3t plus 2t, that makes it 3 minus t. Again with t between 0 and 1. All right. So I think that's enough for lines, okay? That's the first example we dealt with. In the next couple of examples, we're going to figure out another way to visualize these vector functions. By the way, a vector function, here's another name, and actually Maple calls it that way. It's also called a space curve. And the reason why it's called that way, I hope it's pretty obvious. Nothing more to explain, right? It represents a motion in space or a curve in space. One important aspect of these curves, which is important to notice it and figure it out when it's applicable. And so let's write it as a remark, and then we're going to go over an example next time. On the next page. Some space curves or trajectories lie on known surfaces. And it might be important to know the nature of that surface. Like, what is it, if it's possible to actually figure it out, its shape. And mathematically, we can find the nature of that surface. So we can find that surface mathematically by eliminating t from the parametric equations representing r of t, right? The components of the vector function r of t. So let's see what we mean by that on the next page. And again, these examples will be illustrated with Maple when I'm done with the written part of the lesson. All right, so let's take a look at this example. Let's say r of t equals cosine of t, sine of t, and then 1 over t. And let's say, I mean, obviously t cannot be 0, but otherwise, let's say it can take any real number. Or even better, let me think a little bit. Let's say for simplicity that t is greater than 0. So let's make it t greater than 0 to not overcomplicate the situation here. So again, the question is there a surface there where this curve lies on? So the answer to that question, I mean, with some intuition, if you look carefully, you can figure it out maybe, especially if you do a couple of examples like this. But even if you don't know anything about it, one starting point should be to write the parametric equation. So that means the first component, which is the x component, right, is cosine of t, y equals sine of t, z equals 1 over t, right? And remember, a surface as a three-dimensional object will have an equation in terms of x, y, and z. So therefore, if I can eliminate t by any algebraic means possible, then I shall obtain the equation, if such an equation is possible to obtain, in terms of x, y, and z. Now, how do you eliminate t? There is no rule about it. I mean, here you have to basically kind of exploit what you have in the problem. I mean, roughly speaking, you can just basically solve for t, right? So as a general rule, you can solve for t in one of the equations and then plug it into the other two. But this may not be the most efficient way of figuring out what goes on, because you basically end up with two surfaces which intersect that give you this space curve, but it may not give you a good idea of, to visualize actually what type of surface, if any, you have here in the actual problem. What you can notice here, for example, a better way, especially if you deal with cosine and sine, is that I can eliminate t from the first two equations by simply adding the squares of x and y. This is just basically a matter of exploiting the fact that cosine squared of t plus sine squared of t is equal to 1. So that's a much more efficient way or illustrating way of eliminating t. Why is that? Because it tells me, so forget about z for a moment, we get back to that in a minute, but this already, right off the bat, tells me that the curve lies on a cylinder. Again, forget about z for a moment. Imagine that z takes any values. It's not going to take any values, but it'll take infinitely many values. Just by looking at x squared plus y squared equals 1 as z varies, remember this gives you a cylinder. So let's actually do a brief sketch here. This is x, this is y, and this is z. I'm going to start with the cross section, the unit circle in the xy plane, and visualize the cylinder here, right? Up and down. I'm going to just do a brief sketch like that, and let's see what happens to the actual curve. Now let's see what happens to z equals 1 over t. I said that t is greater than 0. Notice that as t, let's start from 0, right? As t approaches 0 from the right hand side, that means t approaches 0 but also positive. Remember from calculus 1 over t goes to infinity. So this curve actually starts way above, almost vertical from infinity as z goes to infinity basically, right? I mean as t approaches 0. And then as t increases, what happens to 1 over t? It decreases. And where it decreases, well, as t goes to infinity, if t becomes very large, 1 over t approaches 0, which is to say that z approaches 0. That means this curve, and by the way, remember x and y move on a circular motion, right? Because x squared plus y squared equals 1 describes a circle in terms of x and y. So you should visualize already that what goes on here is basically a spiral. Let me actually do it with a different color. It's a spiral that starts way from infinity and then spirals down, and these spirals become more and more concentrated toward the bottom, toward the plane z equals 0, toward the xy plane. So they become squished here. So they become, let's see, crowded toward z equals 0, toward the xy plane. Again, with Maple, it'll be pretty obvious what goes on. But I want you to use your intuition to visualize what happens. As x and y moves on a circle, z moves downward all the way to 0, right? Starting from infinity all the way to 0. So the whole motion is essentially asymptotic to that circle in the xy plane. So in other words, the picture is a spiral on the cylinder x squared plus y squared equals 1. And you can see even more than that, it's basically asymptotic toward that circle. That brings me to actually one important definition here. We are dealing with calculus after all. How do you compute, or how do you define something like the limit as t goes to infinity, or let's actually say more generally, limit as t goes to t naught, to some number that can be infinity, either a number or limit at infinity of r of t, right? So r of t being, again, our typical notation, f of t, g of t, h of t. So as far as the limit is concerned, I don't actually go through too much details, I mean, in terms of the general definition. I'm just going to say as a remark, just use every calculus 1 method without proof to compute these limits. Because the limit of a vector function translates to the limit at each component function. So the limit, by definition, the limit of the vector function r of t is the vector given, if it exists, right? The vector given by the limits of f of t, of g of t, and then finally of h of t. Right? So no fancy proofs, there's no need to do anything, just apply any method you learn. If the limit is immediate, compute it right away. But that is the definition. So the limit essentially translates to the limit of each component. In other words, it's asking whether the motion approaches a specific point, or infinity or minus infinity. So obviously, for example, in my previous case, in my previous example, there is no limit, right? Because cosine and sine are still periodic. 1 of t approaches 0, but as a vector function, it doesn't have a limit, right? So I should write here if it exists, right? If all these exist, all three, right? All the three components as a limit if they exist. So here's a quick example. Let's say I want to compute the limit as t goes to let's say t goes to infinity of the vector function e to the minus t 1 over 1 plus t over t plus 1. At this point you should just pause and see if you can answer this quickly from what you know from calculus 1, right? These are immediate limits or nearly immediate limits, right? So if you paused and you checked yourself, took a minute to write it down, you should end up with the answer 0, 0, 1. E to the minus infinity goes to 0. This is like 1 over infinity, which is 0. T over t plus 1 is a rational fraction. Same degree, top and bottom. Limit is the ratio of the coefficients of the dominating terms, right? So that's t over t. Okay, so let's move on with yet more examples on the next page. Okay, so let's do yet another example. I'm going to run this also with Maple. Same question, is there a surface where this space curve lies on? What if the components are cosine squared, sine squared, and t? Again, let's eliminate t. Now, notice carefully here, because the components are already squared, we can use the same trick, but we don't have to square x, y, and z. Excuse me, x and y, we don't have to square them. We can just add them, right? So x plus y equals 1, because they are already, they are squared. I mean, x is cosine squared, y is sine squared, so of course x plus 1 equals 1. Now, what is this representing actually as a geometric figure? So you should recognize that this is a plane in R3 as z varies, right? Now z takes any value, right? I mean, from minus infinity to infinity. And it turns out that because this is a periodic motion given by, I mean, x and y still vary periodically, because cosine and sine are periodic functions, you'll see that. So let's actually sketch that plane. This plane x plus y equals 1 goes to these points of coordinates 1, 0, 0, 1, right, at the on the xy plane. So it's kind of diagonal like that. Okay, so this is basically the plane, and it doesn't go outside 1 and minus 1 because it's outside 0 and 1, because remember, cosine or sine are between minus 1 and 1. So when you square them, they are between 0 and 1, right? Because they are positive. So it varies between 0 and 1, but it's still periodic. So actually, if you sketch the curve, you will see the motion kind of like this. Not too good at this. You'll see with Maple much better, right? So periodic motion, x and y vary periodically according to this cosine squared and sine squared, but everything in a single plane, in the plane given by x plus y equals 1. Here's yet another example. Sometimes let's actually go in reverse basically, right? Because sometimes a space curve can be given as the intersection of two surfaces. And then the question is, can I come up with the vector function representing that surface? representing that space curve. So what if the object is given like this? Let's do an example. Let's say the curve is given by, and remember, intersection of anything, it's basically a system, right? By z equals 4x squared plus y squared, and then y equals x squared. Now think about, go to the quadrics table and see if you can actually figure out what each of them independently represents. Again, independently, and then we take them as a system to figure out the intersection. So if you look at the quadratic table, independently, each of them, you should recognize this as a paraboloid, opened up, right, toward the z-axis. Second one, independently, since there is no z, it's going to be a cylindrical surface with a cross-section given by a parabola, y equals x squared, but it's a cylinder. Now, this space curve is not going to be easy to sketch by hand. Maybe someone can, but I cannot. So I'm just going to give you briefly just to visualize what goes on. So this will be the paraboloid, right? So visualize it here, upward. And with another color, let's say with green again, let's sketch, first of all, the parabola y equals x squared, right? And then imagine that you're going to have that paraboloid, the cylindrical surface cutting upward into the paraboloid. I'm not gonna, it's somewhere here, right, the intersection between them. I can tell it's gonna have probably maybe 2 branches, something like that. But again, this is one of those things in which maple or similar is the way to go, right? Again, we don't have to go overboard with handwritten sketches. We still have to do mathematically, though, the vector function itself, right? So how can we extract the vector function that represents this curve? Because maple may not be able to do that directly, okay? So in this case, it's the opposite procedure, if you want. In the previous procedure, we eliminated t. Here we have to introduce the parameter t. And the parameterization is not unique, but as a general rule, what you want to do is to denote by t one of the variables, x, y, z, and then solve for the other two in terms of t. You can make other uses depending on which formulas are suitable. You have to basically look carefully and choose judiciously which variable you choose. Like, for example, you don't want z to be t, because that'll make it a little bit harder. Excuse me, I have to stop this a little bit. Sorry for the interruption. I'm not gonna re-edit this because it's not worthwhile for a second. We're just about to end the this page anyway. So you don't want to choose z equals t because obviously it's gonna make the algebra harder. The best way in this case is to choose, for example, x to be t, because the algebra is much easier in terms of obtaining the other variables, right? So if x is t, y being x squared, that means it's going to be t squared, and automatically z equals 4 times x squared, which is t, plus y squared, which is going to be t to the power 4. Okay, so the vector function representing this space curve will have the components t squared 4t plus t fourth, and that's one of the versions. But it's important, we'll get back to that later, to remember that parametrization is not unique. So in other words, it's possible to write the same curve with a different choice of the parameter t. So that's it for the written part. We're going to finish with the maple demonstration, and that's going to be it for today's lecture. See you later.